So let's go through number 6 from our Chapter 5 quiz review. So as we look at this definite integral, we know we have to take the antiderivative, plug in 1, plug in 0, and then subtract those two answers. Now as we look at this initially, we might think, oh no, we need product rule here, because I've got this thing times that. But we haven't learned product rule yet, so I need to be able to simplify this so that I don't need product rule. And hopefully we see that we can just distribute this, and then we can do this without product rule. So this can really be simplified before we think about the antiderivative as the definite integral from 0 to 1 of x to the 3/2 plus x to the 1/2. Thinking about that 3/2, this is x to the first, this is x to the half. When I multiply those together, I add the exponents. And then I don't want to forget my dx at the end of that. Now I just use antiderivative power rule, add 1 to the exponent, and then divide. So it was x to the 3/2, adding 1, that becomes x to the 5/2. Divide by 5/2, that's the same as multiply by 2/5. Then originally x to the 1/2, add 1, that's x to the 3/2. Divide by 3/2 is the same as multiply by 2/3. And then I'm going to plug in 1, I'm going to plug in 0, and I'm going to subtract those things. When I plug in 1, I just get 2/5 plus 2/3 minus, and then when I plug in 0, of course, I just get 0. You don't need to write it, I'm just writing it for a visual here. So add the 2/5 and the 2/3, do a little common denominator work, and you see that that is actually 16/15. The next problem here is an indefinite integral. There's no boundaries given for us to plug in. So that's when we know we could have, it's just take the antiderivative, nothing to plug in afterwards. But when you do that, we know that there could be some constant at the end that we don't know was there. And when I take the derivative, it would go away, leaving me with this function. So it's really just like this problem, but I only have to do the first part. I just have to take the antiderivative, nothing to plug in and subtract. The antiderivative of e to the x is, of course, e to the x, because the derivative of e to the x is e to the x. Now this next one is sneaky. The antiderivative of e is not e to the x. This is a constant, so it works just like this was a 3 or a 5 or a 7 or a -24. And the antiderivative of that constant is simply that constant multiplied by the input variable, in this case x. Because I know if I started with e times x, or 5 times x, or -5 times x, the derivative of that just leaves me with the coefficient. So this has to be the antiderivative of that constant. And then, because it's an indefinite integral, we have to have that plus c at the end. Because there could have been some constant out here, and if I take the derivative of it, it goes away, and I don't know what that constant might have been. So looking at my answer choices, that is, for me, the last one here. Yours might be scrambled up differently. Moving on. So now we have to take the antiderivative of this thing with an absolute value. Now we might be thinking, okay, we haven't learned a rule for the antiderivative of an absolute value. So it has to either be like number 6, where I can somehow simplify and get rid of that absolute value, or it has to be like the first couple the first couple definite integrals that we did this chapter, where we draw a picture and it ends up just being friendly geometric shapes. And that's the one that I'm going to do here. There is a way to simplify this and rewrite your absolute value as a piecewise function, and then evaluate the area underneath each piece separately, but it's much easier just to do the geometry here. So we're going from 1 to 4. And the key is, of course, recognizing that this absolute value of x minus 3 is just the absolute value graph shifted over 3 units. And then when I do that, I can see that the area underneath from x equals 1 to x equals 4 is just two triangles being added together. And so if you actually take a second and find the area of those triangles, you're going to get, for the first one, area is equal to 1/2. The base from 1 to 3 is 2. The height, if you plug 1 into that, is going to be 2. And then for this next one, area is 1/2. The base from 3 to 4 is 1. And the height, if you plug in 4, is also 1. Add all those things up, and I think we get 2.5 or 5/2 here. Next one, once again, this is an indefinite integral, so just the antiderivative. And so as I look at that, I might panic for a moment and think, oh no, I need some sort of chain rule because I have secant inside of the squared function, or maybe some sort of product rule because secant squared of x really means secant of x times secant of x. But if you think carefully, secant squared of x is the derivative of tangent of x. So tangent of x must be the antiderivative of secant squared of x. And so there's nothing to do here other than to recognize that and then circle it. All right, I'm going to stop the video again and start again for the file upload, the free response question in a separate video.